Hi, this is our CS330 project, learning protein functional annotation from few shot data via meta learning. So the purpose of this project is to create a model which will be able to annotate proteins with their functional properties using their protein structure data. And one model already exists which does this pretty well, called DeepFry, which is a GNN model which does this. But the problem is that DeepFry requires a lot of data to train, and for many annotations, there exists very few protein examples with those annotations. So what we wanted to do was we designed a model which uses MAML on the DeepFry GNN to teach the GNN how to annotate proteins using only a few training examples for each annotation. All right, now to you, Aditya.
Okay. So coming to the dataset, we use the UniProt KB Swiss protein dataset for our work. The dataset consists of multiple types of proteins. Each protein is represented by a graph where the nodes represent the type of amino acids and edges represent the linkages between them. Now each protein is annotated with a set of molecular function Go annotations. Now these Go annotations describe the properties of the proteins and are crucial for our prediction. Each Go annotation is a binary label of whether that particular Go annotation is present in the protein or not. And it describes whether that protein has that particular property or not. Now over to Keerti.
Okay, so now we're going to go over the metrics we use to measure the classification performance of our model. These are the same ones used by the DeepFry model in their paper. So the two metrics are Fmax and AUPR. Fmax is the maximum protein-centric F1 score averaged across all proteins in the data batch for every classification threshold. And then AUPR is a label-centric area under precision recall curve averaged across each label. Both measure classification performance of our model, but in perpendicular ways. But ideally, we would want both to be high in order to show good model performance.
Okay. To formulate the above problem as meta-learning problem, we do as follows. We create a bunch of train well and test tasks. For each task, we have support set and query set. The support set is described as follows. We sample n Go annotation labels from a pool of labels. Now for each label, Go annotation label, we sample 2K proteins, with K proteins being with the particular Go annotation label and KR without that particular Go annotation label. We use the same Go annotation labels and do the same for query set, but instead of sampling 2K proteins, we sample 2Q proteins with the same setting of Q being with the labels and Q being without the labels. Note that all the proteins in our tasks are unique. Now over to Keerti.
All right, so now we're going to describe the MAML model we used for our experiments. So basically what we did was we created a base GNN model and then applied MAML optimization on top of it. Our base GNN model is based off of the DeepFry GNN used in the DeepFry paper. So this model takes in our protein data in two forms, one of which is the amino acid one-hot encoding, which is the one-hot encoding of every amino acid in the protein, as well as the graph edge index data in our protein graph. So these are inputs to our model. They first travel through graph layers. So graph layers can be any type of GNN layer, such as a graph convolutional layer or graph attention layer. And each of these layers outputs a node embedding for each amino acid. And so we take the outputs of all of the graph layers and concatenate them in the concatenation layer. Then we use the add pooling layer to add up all of the node embeddings for each amino acid to get a single vector for the protein. Finally, we pass that vector through the dense layers with ReLU activations, and then the dense layer with the sigmoid activation in order to get the output, which is a multi-label binary prediction score for each of the Go annotations for that protein. So this is our base GNN model, and then afterwards we apply MAML optimization on top of our base GNN model as described below right here. And then next, we'll be talking about our experiments.
Okay, so the experiment setup is described as follows. We set number of labels to be 3, number of query examples per label to be 1, and number of inner loop iterations to be 3 for all our experiments. We tested this all for number of support examples per label to be 1 versus number of support examples per label to be 3. For our comparative study and results, we have tested mammal trained GCN model, the graph convolutional model just described below before, versus the baseline graph convolutional model that is trained without mammal. So basically, we have a GCN model with mammal and without mammal, and that would be described in the results. All the output measures were the average task Fmax and AUPR, which themselves were averaged across all proteins in the query set of a task, and these are what are presented in the results. Over to Keerti.
Okay, so first we're going to be showing our metrics during a training session. So a mammal training session. So this is for the case when k equals 1. So as you can see, this shows the query support, the query pre-adaptation support and post-adaptation support metrics over the outer loop iterations. And you can see that for both AUPR and for Fmax, the metrics increase as the number of iterations increase for all the query and the support set, showing that the model is actually learning how to annotate proteins with fewer data. And so one thing I also want to point out really quickly is that you can kind of see that the post-adaptation support is growing significantly faster than the pre-adaptation support, showing that the model is actually able to have improved training performance when on the few-shot data itself. And so, now we're going to go into the table, which shows our classification performance results on the test tasks. And you can see that when comparing the non-mammal trained models to the mammal trained models, the mammal trained models have a much higher Fmax and AUPR scores for both both support sizes that we tested. And so you can see that mammal training significantly improves the GCN's performance on few-shot data, which was the goal of our experiment. So our model was successful, but the problem is that mammal training ends up being like extremely slow to run. And so it takes a very long time for us to get results. So while mammal training was successful, we need to look for ways to improve the runtime of our mammal model in order to make it viable and useful. So thank you so much for watching our presentation. Bye.